Hi, today I'm here with Fabio Vanoni, Research Fellow at Polimi, to show you how gamma spectrometry works. In general, radiation spectrometry is the process by which you assess the radioactivity content of a sample of a material, both in terms of radioactive elements present, called radionuclides, and their activity. For our purpose, we will employ two different instruments, a sodium iodide scintillation detector and a GMX hyperpure germanium detector. We are going to analyze the spectra of two radioisotopes of plutonium, namely 238 and 239, since plutonium is a material of great interest in nuclear safeguards. We start with a portable sodium iodide scintillation detector. Among the two, it is the one characterized by the worst energy resolution, but the best manageability. It is important to clarify that the dimensions are not correlated to energy resolution, since the latter depends only on the physical phenomenon by which the instrument reveals incident radiation. The second device is a GMX hyperpure germanium detector. Its crystal is kept at cryogenic temperatures thanks to liquid nitrogen. In contrast to the previous detector, it is unmovable, but achieves outstanding results in terms of energy resolution. Now, we will show you how spectra are acquired via the GMX detector. Firstly, a radioactive sample containing plutonium-239 is placed inside the measuring chamber. Soon after, the acquisition session can start. It must last enough time to ensure sufficient statistics. As we can see, some peaks are forming. They are indicating that gamma rays of a specific energy are much more abundant than others. These are correlated to the decay process of a certain radionuclide, thus allowing its identification. Here, you can see a comparison between plutonium-238 spectra measured with the two devices. The one above was measured with the sodium iodide detector. The difference in energy resolution can be noticed in the peak's width. Less resolution brings to a thicker peak, which may cause them to overlap between each other, making the identification of their source more time-consuming, or, in certain instances, impossible. Moreover, the spectrum acquired from the sodium iodide is characterized by a more intense background noise, due to the absence of a shield, which makes the lowest peaks difficult to discern. Finally, we will use a third device, namely Detective X, to assess the in situ identification of radionuclides. Detective X is a portable hyperpure germanium detector specifically designed to be a user-friendly radionuclide identifier. To achieve a good level of manageability, the cooling of the hyperpure germanium crystal is performed by a Stirling cycle, so that no liquid nitrogen is needed. By bringing the detector sufficiently close to a radioactive source, the count rate and estimation of the dose rate will be displayed on the detector screen, together with a listing of the radionuclide content of the source. The device can also be employed as an in situ spectrometer, either standalone or plugged to a notebook. So, you have seen how to analyze the spectra of two isotopes of plutonium using different devices: a portable sodium iodide and a GMX hyperpure germanium detector. This to assess their radioactivity content, both in terms of radioactive elements present and their activity. Finally, you have been introduced to Detective X, a radionuclide identifier employed in the field of nuclear safeguards. We look forward to seeing you here in our lab to test these devices.